Today we will continue discussing Banach spaces and main properties of Banach spaces which we need in order to consider random elements or probability distributions in these spaces. Last time I finished a lecture with the formulation of interesting problem that LP small and LP capital are not isomorphic when P is not equal to 2. Today we will consider this problem, but in the last part of the lecture. Now I want to discuss two more Banach spaces which we will need and some properties of the infinity dimensional Banach spaces. So let me recall you that we are working with Banach spaces. So this is a linear space with the norm on it, and such that it is complete with respect to this norm. Last time we considered different examples, and to speak about random elements, complicated random object like random processes, random fields, random measures, we need some more examples of Banach spaces. One is very familiar to you. This is the space L infinity. L infinity small is the space of all sequences such that such norm of the sequence, this is super under M, absolute value of the xn is less. Let us note that we of course have to write supremum here, and that with this norm, this space became to be a linear normed space. It's not difficult because this supremum of the sum is greater than sum of supremums. And what is important that relatively to this norm, this is a complete space. This is a Banach space. Why it is so? Because this norm corresponds to the uniform convergence on all set of coordinates. So uniform limit of the bounded mappings is also bounded mapping. Due to this, we have the property that this space is Banach space. We discussed that maybe important feature of the Banach space is its separability or non-separability. In this case, this space is non-separable. Let us remark this. So L infinity is non-separable. And the evident reason why it is so is the following. We can consider coordinate vectors. So let us consider such vectors xn, which consist of all zero coordinates, only one on the place n. Then we have evident element of L infinity for every n, and it is trivial to see that now the norm of xn excuse me, norm of xn minus xn is equal to 1. So we get such one, but this is not surprising. Yes, the same we can do in the any space LP small. But now let's go further and consider much more complicated things, where we can have now not one point, but we have arbitrary sequence of zeros and ones. So now consider x alpha. Here is arbitrary sequence of 0, 1, 1, for example, and so on. How we can get such sequence? For example, we can take alpha from the interval 0, 1 and consider its dyadic expansion. Yeah? Then alpha will be equal exactly 0, 1, and so on. Excuse me, in this case, maybe better to write 0, 0, and so on. Then we definitely will have continuum such x which are different. I don't discuss some cases with two possible dyadic expansion. There are only counted number of such alphas. So we have a continuum set of such x alpha. But exactly as in this case, if we have two alphas, alpha prime, which is not equal to alpha 2 prime, exactly as n, we have the norm of x alpha prime minus x alpha 2 prime is equal to 1. So what we found? We found now non-countable set of elements of our space such that they are on the pairwise distance equal to 1. It means that this space cannot be separate. In opposite case, we can proceed as follows. Let's take a dense subset and let's take our x alphas. Take small neighborhood like 1/3 radius of each x alpha, and take here the point from the dense set. Because if the set is dense, then there must be a point of the set in any neighborhood of any point of the space. Then one can see that these points must be different for different alphas. And we have already uncounted family of the points. This proves for us that L infinity is much more complicated space than the spaces which we considered before. Another example of the Banach space which you will need is the space of silent meshes. So let me consider some measured space X with the sigma field of its subset. This is measured space. And we will organize a set of M with theta. M is a set of all finite silent measures on X. So any element of M with theta can be represented via Jordan decomposition by kappa plus minus kappa minus, where kappa plus and kappa minus are finite measures on this measure of space. This representation is unique, so if one don't like to consider properties of sigma additivity for silent measures, he can say, okay, we just have such objects, and here one can define the norm. One can define the norm, which is equal to total variation. So norm of kappa will be equal kappa plus will be equal kappa plus from M from X plus kappa minus of X. So we have the space of silent measures with the norm of total variation, and it also is Banach space. It is a complicated factor, and also is non-separable for for sufficiently rich space X. I will not check that it is Banach space. Maybe in the course of measure theory, you have the statement that the limited total variation of measures is again the measure. But we easily can construct example of the measures which give us non-separability of space. So M with theta norm is non-separable when X A is rich. XA is rich. What I mean rich? For example, if we consider X equal 0, 1, and A is the usual Borel signal field, in this case we already have non-separable Banach space. Why? For example, one can consider such a family. Again, I will take alpha from 0, 1 and put into correspondence to this alpha the element kappa alpha, which is simply a delta function concentrated at alpha. So let me just recall for a moment. Let me just recall for a moment that delta alpha from the set A is equal to 1 if A contains alpha and 0 if A doesn't contain alpha. So it is evident that norm of delta alpha minus delta beta when is equal to 2 when alpha is not equal to beta. Again, we have a non-countable family elements of our space which have such distance. Okay. By the way, in this case, when x is 0, 1, this space can be identified with the space of functions of bounded variation, again, bounded variation, starting from 0. Yeah. So one can consider in this case our space of signed finite measures as the space of special functions on 0, 1. We will need this space in the future when considering such objects like random measures and their distributions. Now let's go further and let us speak about some properties of Banach spaces, which we also will need. We mainly will be concentrated on the infinite dimensional spaces. So on such where we have infinitely many linearly independent vectors. Yeah? One can take such a system, but I will begin with such situation. Let B be a Banach space with a norm, and I'm considering here just E1, En. These are some elements of B. We will consider A, which is a linear pair of these elements. E1, En. So this is a set. This is a set of all possible linear combinations of these elements. So this is a set like this. Sum from k equal 1 and ak, ek, where ak element of the real set of the real number and k 1 n. What is important here that I need the following fact that L is closed subspace of B. So further statement that L is closed subset of B. This is not very large statement, but we need some statements in our course. So let's be lemma. A is closed. Why this so? Let us check only the case where these vectors are linearly independent. Due to the trivial algebra, one can take here maximal independent system, and then any such linear combination can be rewritten in terms of those independent systems, linearly independent systems. So I will give you a proof only for the case when En are independent, linearly. So I suppose that this N are linearly independent. Then one can consider the following from Rn to our space B. Namely, if here we take the sequence of the coefficients An, then one can put into correspondence to this sequence the sum from k equal 1 to n, ak, ek, which belongs to the our space B. Let us note that this correspondence is continuous. Yeah? Due to the properties of the norm in our Banach space. We know that the norm is continuous with respect to multiplication and summation vector on the number and summation of the vectors. So this is a continuous map. Moreover, I know that if I defined here such a function f of a1, an, that it is the norm of the sum k equal 1 to n, ak, ek, then we know that this function is equal to 0, only if a1 equal an equal to 0. This is due to the our supposition that e1 en are linearly independent. Due to this circumstance, one can say that the function f get its minima on the unit sphere in the Rf. So if S is a set of such that sum from k equal 1 to n ak square equal to 1, then one can check that minima of f on our S is greater than 0. Yes, it is a continuous function, it is non-equal to 0, so it has its minima, and then this minima must be greater than 0. I will put here like C1. Also, it is less or equal than maximum of on S, the same function. Okay, which is I will denote by C2. Now one can take the Cauchy sequence from our subspace A. So let xn equal to sum from k equal 1 to n a k m ek will be Cauchy sequence is Cauchy sequence in B. Then it means that norm of xm1 minus xm2 tends to 0 when m1, m2 tends to infinity. But this norm is equal exactly to f from A M1, I will denote what with L. Yes, with A M2, and it goes to 0, but this is greater or equal than greater or equal than C1 multiply on the norm of A M1 minus A M2. Here I put N. This is due to our construction of the function f. We understand that this can be scaled by multiplication. Then if it is greater than C1 on the unit sphere, then it is greater than C1 on the norm of the its argument. So we have such inequality, and we understand that this sequence of coefficients is also Cauchy sequence, but in our space Rn. And now we already understand that for us this is like very cautious place. Now we have a finite dimensional Euclid space, and we know a lot of things about it. In particular, we know that it is complex, so there is a limit of this sequence. Let's denote this limit by A. So there exists A equal limit when m tends to infinity am, and now it's evident that xm, excuse me, xm tends to the sum from k equal 1 to n ak ek, which belongs to our egg. This is n of the of. So we understand that our finite dimensional space is always closed. It is a good and important thing for us. Now we will consider the procedure of personalization of such spaces, but in arbitrary Banach space. You remember last time we discussed that when we have separate Hilbert space, then one can organize a very beautiful thing like orthonormal basis. One can have orthonormal vectors, and among those beautiful things, we discussed such construction like a projection. So we have some subspace, and we have some vector which does not belong to this subspace. In Hilbert case, one can organize the orthogonal projection of this x onto space A. Here we have, and also the orthogonal complement. So we understand that any vector x from our Hilbert space H can be uniquely decomposed as the sum of two summands. One is the element of our space L, and another one is orthogonal to the space L. So very important thing in this consideration was the existence of orthogonal vectors to our space L, such that we have here orthogonality to any vector from the subspace. So if we consider vectors in the subspace, this vector will be orthogonal to any of such vectors. Yeah? So So, as we have seen, it was a useful statement, and it occurs that it has some analog in Banach space. Namely, let us consider such situation. Suppose we have a Banach space with a norm, and we have A is a linear subspace, which is closed, and such that L is not equal to B. So it does not coincide. It does not coincide with the all space B. With the all space B. Then for every ellipse which is greater than 0, there exists such vector x which belongs B minus L that norm of x is equal to 1 and distance from x to A, which is as usual distance for the point to the set in metric space, is defined like infinite of norm x minus y when y belongs to L, is greater or equal than 1 minus epsilon. So you see what happens. We have no inner product now in our space. We discussed this last time, that in order to have inner product, our norm must satisfy parallelogram equality. In opposite case, we have no such product. So we have no, at least in the beginning, we have no right definition what is the angle between vectors. But we have the notion of the distance. And if you recall the picture which took place in the Hilbert space, when we have orthogonal vector to our space, and if its length is equal 1, then the distance from x to our subspace is equal also 1. And this infimum is achieved on the zero vector. Yeah? So, what is the claim of this lemma? The claim is that we have almost the same situation in the Banach space, but now we have not n, but we have such vector that the distance is at least 1 minus epsilon. So for arbitrary epsilon, we can find such almost orthogonal vector to our space, orthogonal in brackets. And this lemma has the name, the lemma about almost orthogonal vector. Now let's check the proof of this statement. Suppose that we have our space L, and due to the fact that L is closed and L is not equal to P, I can find element X which does not belong to L. Yeah, there exists such X. This is due to this fact, but due to this fact, I know that distance between X and L, I will call it D for simplicity, is greater than 0. This is due to the second fact. L is now what we will do? Let's take some data greater than 0, and then I will find this element y delta which belongs to L, such that the norm of x minus y delta, is greater or equal than d minus delta. Yes, I will choose delta later, but now I just think about delta like about small positive number. Of course, it must be smaller than d. Then I can find such a y delta, and let me consider the element h with delta, which is x minus y delta divided on its norm x minus y delta. Let us see that h delta, of course, have unit norm, and h delta does not belong to L. That's also there. Yes. So now let us consider the distance between h delta and our space L. To do this, let us consider the norm of the difference. H delta minus z, when z belongs to our space. Then what we have? One can conclude that it is equal to, I just use this norm in the denominator, x minus y delta, and here we have the norm of x minus y delta minus z, maybe multiplied on this norm of x minus y delta. Then you see that it is greater or equal than what? This is the element of our L, because y delta belongs to L, z, and this difference too belongs to L. Due to this, this is greater or equal than d, and here I will take the biggest one. So let me say x minus delta. Oh, excuse me. Here I put inequality, of course, must be here. So here I put d minus delta. Okay. Excuse me. Plus delta. Oh, Now everything is okay. Please correct here. Now everything is okay. So we have such an inequality, and what I have to do now, choose delta in such a way that it will be greater than 1 minus it. It's easy to do this because d is fixed positive number and it goes to 1 and delta tends to 0. So we have such form of orthogonal vector to our linear subspace. It is a very interesting, useful from the geometric point of view statement, but for us it is a very bad sign. We will see that it leads to the absence of the Lebesgue measure in the infinitely dimensional space. Exactly this trivial lemma, which we prove in 2 steps, is the main reason why nobody is discussing the Lebesgue measure in the infinitely dimensional space. We will see the reason, but now I already can give you a corollary from this lemma, which gives us a hint why the infinitely dimensional Banach space is much more complicated than usual finite dimensional spaces for us. So, what is the corollary from this lemma? The following fact. Suppose that B again is a Banach space, as usual, such that its dimension is infinity. Then there exists a sequence xn this is a subset of B, such that the first one, for every m, norm of xn is equal to 1. The second one, for every n which is not equal to m, we have the norm between the distance between xn and xm is greater, for example, than 1/2. Okay, so we have such a sequence. You see, this sequence can be very easily obtained in Hilbert space, infinite dimensional Hilbert space. You remember last time we constructed orthogonal systems, and if B is Hilbert space infinite dimension, one can take as these vectors orthonormal system. Then we will have this, and here we will have, due to the Pythagorean theorem, we will have even equality square root of 2. Yes. So this is the generalization, like orthogonal, like generalization of orthogonal system. How one can check this? This statement? I will use the previous one. So, what I'm doing, due to the fact that dimension B is equal to infinity, I can find the set, the sequence yn of the elements of P such that the any finite number of elements of this sequence are linearly independent. It happens due to the following reason. Since it has infinite dimensions, there exists infinite system of linearly independent elements such that any finite subset is linearly independent. And from this system, we always can have a counted subset. This is a statement from the set theory. So one can find such a sequence. Then what I'm doing further, I'm considering for every n greater than 1 and fixed, I'm considering Ln, which is now closed subset of Ln plus 1. And Ln is as before equal to linear span of Yn1 Yn. Then this is a strict inclusion because of independency, and what we know that Ln is closed subset of this one. So I can use our previous lemma about almost orthogonality and find such a sequence due to the previous lemma. I'm finding such a sequence of xn z. Xn plus 1 will belong to Ln plus 1. Z norm of xn plus 1 will be equal to 1. Distance of xn plus 1 to Ln will be greater or equal than 1/2. Now I'm taking epsilon equal to 1/2. Then when completing this procedure, I will get the sequence with desired properties. Why? Because you see, due to this inclusion, the previous elements of the sequence xn belong to Ln. So distances, pairwise distances between the elements of the sequence will be no less than 1/2. So that's all. Now we understand that we can find such sequence, and by the way, it means as a corollary, we will discuss it further, but now we can say that the unit ball in infinite-dimensional Banach space is not a compact set. So infinitely dimensional Banach space or Hilbert space, it doesn't matter now, is not locally compact. It is very important and useful for understanding difference between finite and infinite dimensional spaces statement. The unit ball, the infinite dimensional space is not locally compact. Okay, now let's go further and let's think how we can discuss random elements or equivalent the distributions of random elements in Banach spaces. If we think a bit about this, then we have to understand the following. when we want to consider some complicated random object, first of all, we must have the tools to discuss properties of this object and to define it, because right now we don't know what is random. What is random now? Because you remember the main definition where we began strict formal probability theory begins from the following. A random variable is the measured map from omega to R or to Rn. Yes. Now what we must write? We must write here B and say is measured. Now this is a question: how we will define measurability and how we will discuss it. It is more important because we can propose a very complicated construction, but then how to work with this construction. We have to understand what to do in this case. Some of you, of course, say, oh, it's trivial. We already know random process theory, and we know the very nice example of such situation. For example, if we consider B as a space C01 with uniform norm, one can forget about random elements, but consider random process with the continuous trajectories. So psi is continuous random process on 0, 1, and it must be the random element of this C01. Yes, and how we discuss it. As usual, we just forgot about all this sophisticated construction and just consider psi T1, psi Tn for T1, Tn from 0, 1, and say here we have random vector, then we have a finite dimensional distribution, and this family of finite dimensional distribution finally gives us all information about possible properties of the random process psi. What was crucial? This one. We can speak instead of very complicated object. As I told you last time, due to inflow theorem, it contains any separate Banach space, so it is very complicated object, and we will face a lot of troubles in the future related to this space. But one can avoid all these things and just speak about such sets of values, the concrete values of argument. Yeah. Maybe we can try to do the same here. So what will be the main idea? What can be the main idea when discussing random elements in the space B? Maybe we will want to have some like value of the element at some point. I am almost done with this lecture, so just a little bit. Maybe we need something instead of values of psi at the point. And one can do this using the notion of continuous linear functional. functional form. And it occurs that this is exactly appropriate language on which we will discuss random elements in B. But before to do this, we have to be familiar with these objects, and we will do this next time, and we will see how it helps us to distinguish non-isomorphic Banach spaces. For today, that's all. Thank you for attention. If somebody have questions, please.
Yes, I have a question.
Okay.
So very naively, so you pose the question. So we have a mapping from omega to a Banach space B. What does mean measurability for this psi from omega psi?
Yes, exactly.
Random element. So if we have a Banach space, this means that we have open balls, we have a topology, we have Borel sigma algebra. So why should we?
Exactly. This is very good question, and the answer is following. There are two reasons why we pay attention to this question. First one is the following. If B is non-separate, Borel sigma field is very rich.
Okay.
Very rich. And working with it, we are not guaranteed even to the following things. Let me show you. Suppose that B is non-separate. Then one can think about different functions from B multiply B, excuse me, to B. And maybe you remember that when we discuss the case that, for example, sum of random variables or random vectors became to be random variable or random vector, we use that if we have a good function here, we will have again from two random elements we get new random element. The idea was that we can represent the open set as a union of counted number of balls, and it is not true now. For example, if you take in this sense, if we consider two bounded random operators, because the space of random operators is Banach space with respect to usual norm, and if we have, but usually it is non-separate, yeah. So if we consider two random operators in this sense, let's take a product.
Let's take what?
Product. Just product, and try to prove that it is also random.
Okay.
You see, this is the first problem. Another problem, as I said, it's better to speak in terms and in the language of objects which we can just take in our hands. So let us suppose that we want to have something like characteristic function for this random element. What it be? This is application of continuous linear function to psi, then exponent. Then what we need? Maybe we want to have the statement, and we will discuss it. We want to have the statement. Characteristic functional uniquely defines the distribution. To have this, we need the statement that the sigma field generated by the linear functionals is the same as the sigma field is the Borel sigma field. This is also a question.
Okay.
You see?
Yes.
So we have a lot of technical questions which arise due to the infinite dimensions.
So sometimes as a corollary. So sometimes it is reasonable to consider a smaller sigma algebra than the proof.
Exactly. Yeah.
Just exactly that one which makes our characteristic functionals working.
Yes, surely, in order to work with it and so on. We will see further.
Okay,
We will see
thank
further how it works. Okay, thank you for the question. It was in appropriate place. Thank you. Okay, so thank you for your attention. Bye, and for participants of the seminar, I just will send